All right. I actually forgot to record last night's meeting, so here we go with take two of this lecture. Sorry you can't hear any of the questions that were asked during the meeting, but at least we'll have this. Um, so today we're going over a little bit of rocket engine theory, some of the core concepts of thermofluids classes, and then how they relate to rocket engines. This is going to be a very dense um, presentation and a lot of new concepts you might not be familiar with. Again, as I said last night, we're not doing any more working breakout sessions. You don't need to apply this anywhere. So this is just for you guys to absorb and take in and learn. And don't be concerned about understanding everything. Um, I mean, it would be nice to understand everything, but realistically, the freshmen, this is advanced stuff. So I would just recommend watching this one now, maybe watch it a second time, try to take in as much as you can. Um, and then we'll have these recordings somewhere in the Google Drive forever. So, once you take a thermofluids class or two, come back and this will start to make more sense. But yeah, I've tried to make this as digestible as possible. It's not easy, but anyway, with that disclaimer, go ahead and get started. This is broken out into three parts, um, as you can see, and we're just going to go, each part is going to be its own meeting. So, first, we're going to go the first two slides here, just a little bit of term definitions of like stuff we're going to be using in all three of the parts. So the first concept that comes up quite often is the idea of steady state. Basically, it just means that nothing is dependent on time. There are no time derivatives of anything. So this would be, in our case, in the rocket engine, the amount of mass flowing in is the same as the amount of mass flowing out. You have no buildup of mass. Same thing with energy. Energy flowing in is the same as the energy flowing out, although it will be flowing out in different forms. So you don't have any buildup of energy inside your system. So that's basically steady state. Another big concept that's used a lot is the idea of a control volume. And basically, I don't know if you've heard of systems versus surroundings. That's a big concept in thermodynamics. Basically, you have a system that you're analyzing, and we just kind of draw an arbitrary volume around that system, and everything inside that volume is your system. Everything outside is the surroundings. And anything that crosses that control volume boundary, we analyze as mass flowing into the system, mass flowing out of the system, energy flowing into the system, energy flowing out of the system, that kind of stuff. If you'll remember when we did our flow sims, when we put the lids on, and I don't know if you remember, there's like the kind of like grayed out or grayish transparent box that shows up around that. In SolidWorks, that's like your computational domain where it actually calculates stuff, but that can also be thought of as the control volume. Since you have stuff flowing into that computational domain and stuff flowing out of the computational domain, that can also be thought of as a control volume. Another thing I want to talk about is variable convention. Since, capitals, lower cases, dots all mean different things. So capital letters are total values. So I put enthalpy here as an example. H represents the property of enthalpy, and that's the total enthalpy that's present in a system, and the unit for that is joules. So that's just total in here is joules for enthalpy. Lowercase letters are specific values, which basically just means it's per unit mass. So if you take that enthalpy value from here and divide it by the amount of mass in your system, that is lowercase h enthalpy per unit mass, and the unit for that would be joules per kilogram. The same goes for almost any property: energy, total energy measured in joules, specific energy, joules per kilogram. Dot notation is something we've talked about before. Basically, it's just a time derivative or something per unit time. Most often you'll see this with mass flow. M dot is flow of mass per unit time. You'll also see this a lot in heat flow. I know in the lecture before, I think we use a lowercase q to represent flow of heat, but in thermodynamics, you'll generally see capital Q dot is the flow of heat per unit time, flow of energy per unit time. So that's what dot notation is. Okay. And now just some variables that we're going to use throughout this, and I'll go through these pretty quick since a lot of them you'll probably already be familiar with. T is temperature. In most cases, we're using temperature in Kelvin. P, capital or lowercase, is pressure. This is one that specific versus total doesn't really matter. Pressure is pressure. Lowercase and cursive V is specific volume. I don't know if you guys may not have seen this before. It's basically just the inverse of density, where density is what mass per unit volume. Specific volume is just volume per unit mass. 1 over the density. This is just generally used with gases instead of density for some reason. That being said, rho, which kind of looks like a P in its variable form, is density, again, mass per unit volume. Gamma, or K, is the specific heat ratio. We'll get into more exactly what the specific heat ratio is later. Hopefully everyone kind of knows or has seen this before in the CEA results. It's something that's there. I don't know if we used it, but specific heat ratio is there in the CEA, and CEA calls it gamma. Some textbooks call it K. R is the specific gas constant. So I'm sure from chemistry or wherever you're familiar with the gas constant. R generally, at least in this PowerPoint, anytime you see R is referring to the specific gas constant. This is one case where it breaks our convention, where a capital R is still specific gas constant. V is velocity. Q is energy transferred by heat. W is energy transferred by work. In the case of thermofluids, that work is represented by pressure times change in volume, whereas I'm sure people are more familiar with the physics definition of force times distance. Yeah, I don't think this comes into play with rocket engines so much, but just W is work done by the system, and it's covered up here, so I'm going to stop wiggling my mouse. M is Mach number. That is just the ratio of the fluid's velocity versus the fluid's speed of sound. I think we've seen this before. Yeah, capital M is Mach number. All right, so the first part we're going to talk about is a little bit of thermodynamics. The first few slides of this are just a bit of background into thermodynamics, and they can be kind of dense, so just bear with me. I'm going to try to go through them quick and make it as simple as possible without getting into like the weird definitions. And then after that, it will be more of like how thermodynamics relate to the rocket engine and how CEA kind of does what it does after it does the chemistry part. So the first concept is entropy, which is a fairly complicated concept. So I'm just gonna. We don't need to know too much about it. Just that, in our purposes, entropy is kind of just a measure of irreversibility. Um, Usually, it's thought of as kind of disorder in a system. Um, Basically, if you have entropy generated, um, that process can't be undone. It's an irreversibility. Um, so entropy can always be generated, and it can be transferred through a heat interaction, but it can never be destroyed. Entropy always increases. Um, so the most important parts to get from this entropy slide are the different types of processes in relation to entropy. So a reversible process, or an ideal or a real process, as it's also known, is a process that has an entropy generation of zero. No entropy is generated. Everything can be undone. In our example of rocket engines, um, or even just any kind of flow, if you put it through a converging nozzle and then put it through a diffuser, forget the whole um, rocket engine that accelerates everything. Um, Think of it just like water going through a converging and then diverging nozzle. It's not going to be supersonic or anything, but what happens is in the nozzle, the converging section of the nozzle, the water speeds up, its pressure drops. Remember Bernoulli's principle, and then when you put it through the diffuser, the diverging section of the nozzle, it slows down, pressure increases. In a reversible process, that pressure will return exactly the same. The velocity will be exactly the same as it was in the inlet of the converging section of the nozzle. Um, none of that energy is lost to disorder. I'm gonna come back to isentropic process. I'm gonna talk about an irreversible process first. So an irreversible process has entropy generation. Some of its energy is lost to quote unquote disorder. Um, so basically, visualizing that again with the nozzle and the water, it would be like if you put it through the converging section of the nozzle and you accelerate the water, and then you put it through a diverging section of the nozzle that's exactly the same, except this time it doesn't return to the exact same pressure or the exact same velocity. It's a little bit lower in pressure and it has a little bit less velocity. The energy has decreased because some of it has been lost to entropy or disorder or however you want to imagine entropy. Um, so that's just an irreversible process. There is no way we can destroy, quote unquote, the energy or the entropy that's been created. There's no way to go back to that original state um, unless you do outside work on it. Um, So with that, an isentropic process is one that is both reversible and there is no entropy transfer. So that means an isentropic process, the entropy stays the same. There's no entropy generated and there's no entropy transferred into the system or out of the system. Um, and that's kind of, these two are kind of like a square is a rectangle, but a rectangle isn't necessarily a square. All reversible ideal processes are isentropic, but not all. Wait, is that right? Ah, no, it's the other way around. All isentropic processes are reversible, but not all reversible processes are necessarily isentropic. Sometimes you can have a heat transfer in and out with a reversible process, and the entropy will change, but no entropy is generated, and that would be an example of a non-isentropic process, but one that is still reversible. Anyway, sorry about that confusion. So that's all you kind of need to know about entropy. and we'll get to how that relates to stuff with rocket engines later. Um, so specific heats. I'm sure most of you are familiar with the term specific heat capacity. You know it as the variable C. When you're dealing with solids and liquids, that's one value. Specific heat capacity relates the energy with the temperature. For gases, that concept gets a little bit more complicated. There are two different specific heats. Um, one CP, specific heat at constant pressure, CV, specific heat at constant specific volume. They are kind of as it's implied. The CP, specific heat at constant pressure, relates the energy and temperature if you're heating it at a constant pressure and allowing it to expand. CV is the same thing, relates the temperature and the energy while you're heating up a gas at a constant volume without allowing it to expand. So if you remember for the ideal gas law, this would mean the pressure would increase even while the volume stays the same. More specifically, that you don't really need to know, just a kind of interesting thing is oh, I think I skipped a slide. I did skip a slide. We'll just talk about that next. So CP relates the change in enthalpy versus change of temperature. CV relates the change in internal energy versus temperature. And I know I skipped that slide. I'm going to come back to that right after this. It will make sense in a second. So as I said, both of these values are just the same for liquids and solids. So that's why you can just say specific heat without differentiating for those. And then the big thing to know is that K, gamma, the specific heat ratio, is literally just the ratio between these two specific heats. So now you know what this variable is when you see it in the future. So now I'm going to go back to the slide where we talk about the difference between enthalpy and internal energy, because those are very similar and it can be kind of confusing. So internal energy, as it implies, is the amount of energy that's contained in a system. Now that amount of energy is fairly arbitrary. We have to define that relative to a reference state. That can either be most commonly, well, it could be anything you want realistically, but most commonly you'll see it in sources as reference to 0 degrees Celsius or 0 Kelvin. 0 Kelvin is more ideal because if you reference 0 Celsius and you have something that is below 0 Celsius, you can actually have a negative energy, which is kind of weird to think about. But I mean, energy is just defined relative to a reference state. So it is possible. 0 Kelvin is absolute zero, which means if your reference state is 0 Kelvin, energy is zero, and you cannot have any negative energy there because absolute zero temperature also corresponds to absolute zero energy. So enthalpy is a slightly different way of measuring the energy in a system. The way it's defined is internal energy U plus PV. Remember, I was saying earlier in thermodynamics, we define work not as force times distance, but as pressure times change in volume, which if you think about it is fairly similar. Pressure is force per unit area, volume is kind of just like distance per unit area, if that makes sense. So yeah, the PV term here represents the work done to displace the system's volume at the system's pressure. It's kind of just like an energy of existence, so to speak, that isn't factored into the actual internal energy. since internal energy is more like all the, kinetic energy of all the particles, similar to temperature. Again, this is also usually referenced to 0 Celsius or 0 Kelvin. And enthalpy is used rather than internal energy because this term U plus PV just kind of showed up a lot in thermodynamics, and people were like, hey, we should give it its own variable. So yeah. All right, I think that's it. Yeah, that's it for the kind of background on thermo slides. And now we can actually get into the how this relates to rocket engines. So as we said, control volumes earlier, if we have a control volume here, and it's also in steady state, we can do a balance on the amount of energy going in and out of the system versus the change in energy versus change in time. So in steady state, this change in energy versus change in time is 0. So we pretty much just do this energy balance on the control volume to make sure that this is true. This is the main equation you'll see in thermodynamics. If you're talking about anything from rocket engines and nozzles to power plant turbines, boilers, all kinds of stuff that you'll see in thermodynamics. So basically what all these terms are is Q dot, remember, is rate of heat transfer in or out of the system. W dot is the rate of work done on the system or by the system. And then you have these two terms here that go with M dot, which is mass flow. So mass flow into the system, mass flow out of the system. Both of those mass flows will carry energy with it, and that energy comes in different forms. I'm just going to talk about in for now, since out is pretty much the same. So with the mass flow, you have the enthalpy of the flow. Remember, that's internal energy plus the energy of it takes to take up the space that it does. You have this term here, velocity squared over 2 is the kinetic energy term. 1/2 mv squared. They just pulled out the m here. And then gz is the gravitational potential energy term, mgz, and I just pulled out the m again. So this term and this term are just the energy that the flow carries with it in and out of the system. So together, all of this is kind of just a sum of all the energy flowing across the boundaries of our control volume. So this equation, as I said, applies to rocket engines. And there are a bunch of assumptions that we can make to simplify this equation. So the first is conservation of mass. There's only one inlet, there's only one outlet in a rocket engine, and we know there's no buildup of mass in the system. So we can say that inlet mass flow equals outlet mass flow equals just one constant m dot. We also can assume that since, our outlet flow at the exit of the nozzle is going supersonic, Mach 2, Mach 3, and the inlet flow is going considerably slower than that, we can assume the inlet velocity is negligible compared to that this term is very, very small, and we can kind of just assume it's 0. I'm going to start drawing on here. So that is 0 because we're in steady state. We just said that this term we can assume is 0. We can also assume that the change in gravitational potential energy is relatively small. Doesn't matter if the engine is aligned vertically, horizontally. This is just a very small energy compared to especially the kinetic energy and the enthalpy. So we can assume both inlet and exit are 0. We can also assume the combustion flow is adiabatic. Oh, that's another term I didn't discuss in the background section, but adiabatic just kind of means there's no energy transfer in or out. Basically just Q dot equals 0. This assumption is not necessarily true. We'll get to that later in the limitations of this model in this equation. But for now, we're going to assume that it's relatively small and we can kind of just say it's 0. We can also assume that no work is being done on or by the fluid. Basically for this, for flow, you kind of need a turbine in order to do work on or by the system. Turbines and pumps are the main drivers for flow in the work. So we're saying that there's no work being done on or by the system. So this term is 0. And as I already put here, the engine is operating in steady state. So this term is 0. So now we're only left with these terms here. And if we write them out, 0 equals, and remember these are the same, so we can kind of just pull that out. So m dot H inlet minus enthalpy at exit. This gets distributed, so it's minus the velocity squared over 2 at the exit. Since this is equal 0, if we divide that over, that just cancels. And then we have H inlet minus H exit minus V squared over 2 equals 0. So now we can rearrange this. I have this on the next page. So clear drawings. So we can arrange this to say that H1, H inlet minus H2, H outlet equals the kinetic energy term at the exit. So basically what this means is enthalpy in minus enthalpy out is the kinetic energy of the exhaust gases. Basically, the rocket engine takes the large amount of enthalpy from combustion gases and turns that into a large amount of kinetic energy of the exhaust. And that is the main function of the rocket engine. We want to maximize this term and minimize this term. And from the combustion side of things, we want this term to be as high as possible. Yeah, so that's basically what a rocket engine does. But now, how do we get these terms here? What do I have next? Yeah. Basically, H1 comes from a lot of chemistry. I don't know if in your chemistry classes you've done combustion stuff and reaction stuff and like heats of formation and all that good stuff. But where I'm not going to get into the specifics of that per se, just more like the thermodynamics of it. But yeah, CEA starts by doing a bunch of chemistry to find this H1 value. And now we're going to talk about how it figures out what these values are going to be. So, as we went over before, isentropic processes are completely reversible. So we have what's called isentropic ideal gas processes. So again, as isentropic processes are reversible, and thinking back to the example before with the nozzle accelerating, decelerating, doing whatever with gases, If we assume that that's an isentropic reversible process, whatever the nozzle does can be undone. And basically you can correlate the properties, the fluid properties from one point in the nozzle to another, assuming that the process to get between those points are reversible. So that's where these equations come in. I'm not really going to go over how they were derived, but just they exist because with an isentropic process, you can correlate those two. So it's basically like if you were to take the combustion gases in the chamber and you flow it through a converging section of the nozzle, not quite to the throat, so it doesn't do all the supersonic stuff when you diverge it. So when you bring it to the throat, or when you put it through the converging section of the nozzle, what happens is pressure goes down, again, Bernoulli's. I believe temperature would go down considerably too, and the flow increases a lot. Now, if you re-expand that back to the chamber diameter, all those properties will go back to how they were at the chamber. So yeah, you can correlate between those if you just know the specific heat capacity and these equations. And then we usually, in these equations, the not variable here, we usually relate any point in the nozzle to what's called the stagnation conditions or stagnation properties, also known as total properties. Sometimes you'll see, most of the time, if it's a sub-zero, it's stagnation. Sometimes they'll show it as a sub-T, that just means total, which is the same thing. That can be kind of confusing. But basically, it's if we take that nozzle and expand it to like an infinite area and pretty much just bring those gases to rest, what are the temperature, pressure, and density? Those are the stagnation conditions. So if we know the stagnation conditions, we can figure out what the temperature, pressure, density are in any other point of the nozzle, as well as, or at least we can relate it between the Mach number. Yeah. Okay. So now CEA, once it has the inlet conditions, uses these formulas. It assumes, hold on. Yeah, so CEA uses these relations to find all the properties throughout any point in the nozzle once it does all the chemistry stuff to find the inlet enthalpy and temperature and pressure and density and all that. So basically, if we assume that the chamber pressure, temperature, and density are the stagnation conditions, so this T naught, P naught, rho naught, if we assume those are if these stagnation conditions exist in the chamber, and then we know about the other parts of the nozzle. We know at the throat, Mach number equals 1. We know the specific heat ratio, gamma here, is a property of the gases. So we know that. We know Mach number equals 1. We know the stagnation conditions from the chamber. You can find temperature, pressure, and density at the throat relatively easily. And then for the exit, what you know is, remember we gave CEA a pressure ratio as well as the chamber pressure. So using that ratio, it can find the exit pressure, which means it knows, again, the specific heat ratio. It knows the chamber conditions, which are we're assuming are stagnation. And we know the pressure at the exit. And using that, you can solve for the Mach number. And once you have that Mach number at the exit, you can plug that into these other equations And using the chamber conditions again, you can find the temperature and density at the nozzle exit. So that's kind of a brief overview of at least the thermo part of how CEA works and how it uses these ideal gas relations to find properties in different parts of the nozzle. Um, and it can find the basically from the Mach number, you can get this term, and you can see the difference here. Um, yeah, so these are more of the equations that CEA, or if you wanted to do CEA by hand, you would use to solve for kind of designing the rocket engine and like figuring out all the parameters and stuff at different points of the nozzle. Um, this equation we don't so much use in the design process of the engine, but this is just to illustrate kind of what happens in a rocket engine. It takes a large amount of energy from given off by combustion and turns that into a very high velocity term in the form of kinetic energy. So all the heat energy from combustion and chemical potential energy in the fuels, once it's combusted, the nozzle will turn that into a very high kinetic energy and a very high velocity. So, as I mentioned before, we make a lot of assumptions here. Assumptions are good. Assumptions are great. They make your math easier. You just have to need to know what the limitations of those assumptions are and whether it's um, a close enough assumption that you can make it and still expect relatively accurate results. And I mean that's all engineering is understanding what's actually happening and then figuring out what assumptions you can make to make the math easier. And then if they don't work, go back and take away some of the assumptions until it gets better. Just a little life tip on figuring out what engineering actually is. So anyway, the first assumption that we made is that the inlet velocity was negligible. If we go back to, why is that? There we go. If we go back to this equation, we assume the inlet velocity was negligible. And also because we assumed inlet velocity is near zero, we said that we can assume stagnation conditions in the combustion chamber when we're doing these equations. So in general, that is a good enough assumption, provided that the flow is going slow enough. And that is actually something we can control using the chamber cross-sectional area. We'll get to it in the next lecture, but in fluids, there's a thing called the continuity equation. I'm sure you've all heard of it as m dot equals rho AV, mass flow equals density times cross-sectional area times velocity, and that stays constant throughout any kind of nozzle. So, increase the cross-sectional area, we can decrease the velocity in the chamber. So that is where we got the parameter for the ratio between throat area and inlet area, cross-sectional area of the combustion chamber, where we got that 4 or greater. 4 is kind of the lower limit of where this assumption is accurate enough that we can use it. Anything above that is going to be more accurate until you get to a certain point where your combustion chamber is just a really wide pancake, and then you don't have complete combustion. It doesn't fill the whole chamber, all kinds of stuff. So that's why we said 4 or more. And I know a lot of you came to us saying, "Oh, it looks really long and skinny. Is this right?" And that's why we were like, go ahead, make it wider, make it more aesthetically pleasing. It just has to be greater than 4 for this assumption to be valid. another big assumption, another huge assumption that we made, considering we did an entire lecture on managing the heat transfer out of the combustion flow. We did assume for the math, and CEA also does assume this, that there is no heat transfer out of the combustion flow. And again, that's not true. Um, so that means some of this inlet enthalpy is lost um, to heat. I think if you do it out, Q ends up, I don't exactly know where it ends up. Q out is negative. So you have a negative Q here. So they would show up as a plus Q dot here that takes away from this velocity term. Um, so yeah, using that assumption means that in reality, when we go to test this, um, the exit velocity is going to be lower than a little bit lower than we expected. We're not going to have quite as much thrust as we expected, but that's okay. That's all in the design process. In order to trying to calculate that Q out, as you saw in that lecture, is fairly complicated, and it's much easier to just assume that that Q out value is zero and deal with a little bit lower efficiency than we were expecting. That being said, one way you can mitigate that is using regenerative cooling. Um, as we talked about during the heat transfer lecture, regenerative cooling is basically cooling with the fuel before it gets injected and combusted. So basically, what you're doing there is the heat is transferred out of the combustion flow, it's transferred into the walls, and then it's carried away by the fuel, which increases the enthalpy of the fuel before injection and increases the enthalpy post combustion too. It carries that with it through the combustion process. Um, and that's why regenerative cooling is known as regenerative cooling. Basically, instead of taking the heat transfer out of the combustion chamber and dumping it into a coolant that's being, carried away and in a recirculation loop, um, that energy that's being lost, a lot of it is going back into the fuel and back into the engine, so you're not losing as much. And the last one, another big assumption, obviously, if we're using the isentropic ideal gas processes, we're assuming that the flow is isentropic. And in real life, nothing is isentropic. You can get close to it, but you can't quite get it. So remember, I was saying in an isentropic flow, you would have a converging section of nozzle. It would accelerate the gases, bring down the pressure, bring down the temperature. You would, be converting this H into velocity energy. And then in theory, if you're doing this before the throat, if you expand the flow again, you'll turn this velocity energy back into enthalpy. But we have a thing called entropy and disorder. And basically, there's another term here. Some of that enthalpy energy, when you put it through the converging section of the nozzle, is going to be, some of it's going to go to velocity, some of it's going to go to entropy. And entropy, remember, cannot be recovered really. So when you go to turn this back into enthalpy, it's not going to be quite the same enthalpy. So it's not going to have quite the same temperature. It's not going to have quite the same pressure as it did before, and you can get less energy out of it. So again, this is just like with the heat being lost. Some of that enthalpy is not going to be turned into useful kinetic energy of the exhaust gases. just going to turn into entropy, random disorder, and your exhaust velocity is going to be slightly less fast, slightly slower um, than you calculated, and again, you're going to get slightly less thrust than you calculated. But the process of calculating entropy is, I actually don't even know if there is a way to estimate the entropy that will be generated. I think you just kind of have to measure the measure the actual and compare it to the isentropic assumption, and then figure it out that way. So yeah, I mean, we just assume isentropic because there's no easy or possibly no way to try to account for those losses. Um, so it's easier to just assume it's isentropic and deal with the losses later. All right, so that is part one, all about thermodynamics and how they relate to rocket engines. Um, Again, don't worry if some of this went over your head. That's completely fine. This is really dense material. It might take a few watchings to get. It might take a few watchings and taking our Northeastern's course on thermo in order to understand that. That's fine. I certainly didn't understand this the first time I read it in a textbook. But hopefully, the way we've presented it here has made it easier to understand than just reading the chapter in rocket propulsion elements. If you have any questions about this, feel free to ask me or Arun or any of the mentors, Mark or Sam, in the Discord. You can put it in the intro to prop general channel and ping one of us. You can DM us, ask questions. We love answering questions. You guys are the future of the project, so it's in all of our interests that you guys actually learn this stuff. So yeah, we want to help you learn and get excited about rocket stuff. On Thursday, we'll be doing part 2 on fluids.